We're going to start chapter 8 today. It's Wednesday, the 8th of April. It's the first class after the exam. With respect to the exam, I haven't had an opportunity to look at it yet. We won't have any classes here on Friday, so I have a day off on Friday because of the religious holiday. So hopefully that day will give me an opportunity to catch up on some of the grading, particularly the exam. I will mention the paper, right? I put a guide slash rubric up on the Joule website to try to look at these 100 points that can be earned if you choose to write the paper. It is an optional assignment, as I mentioned, if you choose to do this. Some students, like I said, are wanting the opportunities to gain points in the class in other ways besides the exams, and that's the way we get most of the points in the class. And so this paper may be a good opportunity to do that, but I should reiterate, it's not extra credit. You won't get some credit just for doing something. If it's not of good quality, it'll be graded as such. So I think that hopefully the rubric slash description that I posted will be helpful. If you have questions on anything specific to that, let me know. But everything like due date, format, all of that stuff, it should all be on there. I will post tomorrow, if not Friday, a small weekly concept check, right? Like I've done on Joule with some, multiple choice questions. It may be abbreviated, obviously, because we will only have this one class of content to cover. But I do think it helps. It helps you keep up, and then when we get started on Monday, we can hit the ground running. So look for that, right? That'll be up, if not tomorrow, for sure by Friday at some point. And then I'd like you to turn it in by the end of the day on Monday, just like we've been doing. Okay. So I'll email you, I think, when that goes up. The benefit to talking about the chemical synapses that we've talked about and the signaling pathways that we've talked about is it'll allow us to then get into chapter 8, which is synaptic plasticity. Okay. Plasticity, the term, right, is really defined as a change in, well, maybe we write this up here. Plasticity is really a change in, I guess we'll call it the wiring although that's maybe not the most scientific term, as the change in wiring of the cells that communicate with chemical synapses. Okay, so just like you can rewire a computer or rewire a stereo, the wiring, quote unquote, of the nervous system can be changed such that we can either increase or decrease signaling. All right. Now, this is usually broken up into short and long-term mechanisms. So if we look at those that are short-term, right? Usually what short-term plasticity involves is a change in neurotransmitter release, okay? So if we look at, again, we can not only divide this up short-term, long-term, but also is it increasing or decreasing neural output, right? So mechanisms that increase neurotransmitter release or enhance neurotransmitter release typically are caused by persistent calcium. So increase in neurotransmitter release we're over here, prolonged or persistent calcium levels at the axon terminals. Okay. Whereas decreases, right? So we can have short-term increases, the idea being that calcium at the axon terminal is present longer. This allows more neurotransmitters in the vesicles to be released, and that will increase the strength of the signal, right? Decreases typically involve a reduction in signaling due to the depletion of vesicles. If you remember, right, back to chapter 5, we talked about how there's a reserve pool of vesicles. And once that reserve pool is depleted, or as it's depleted, I suppose, there'll be a reduction in signaling strength. Now, this, you would imagine, would be activity dependent. And what I mean by that, dependent, is that if a presynaptic neuron is continually stimulated and continues to release neurotransmitter via vesicles, that activity will lead to depleted release over time, right? That pool will decrease and decrease and decrease. So that's what I mean by activity dependent. The first sort of shot of activity, that reserve pool is full. But if that activity is prolonged in the presynaptic neuron, eventually the pool gets deleted and we see short-term decreases in neurotransmission. If we consider the long-term plasticity of the circuit, long-term plasticity is changes in neurotransmission that are persistent, right? And so what does long-term mean? I know that's an open-ended term. Really, we think of a change of 30 minutes or longer. So can we still see this effect, the change either up or down, either increase or decrease in transmission for 30 plus minutes? So it lasts 30 minutes or more. Okay. What happens in this case, what underlies long-term plasticity, are often changes at the protein level. And oftentimes it's the glutamate receptors that are involved, right? So put in parentheses, often it's glutamate receptors. And so maybe this is referring to phosphorylation or dephosphorylation. Maybe this is a change in their expression. Maybe we increase the number of glutamate receptors or decrease them. Maybe we internalize them, right? We get rid of them. Any of these things, but glutamate receptors are going to serve as a central focus as we go forward throughout this chapter. Okay, so let's talk about these short-term mechanisms in a little bit more detail. So one short-term increase in neurotransmission is called synaptic facilitation. And synaptic facilitation involves a rapid increase in synaptic strength. So we're talking, right, time frame rise. It's rapid. It's going to be on the order of milliseconds. So a rapid increase in synaptic strength. When two or more action potentials, so these are the conditions now, when two or more action potentials, we would abbreviating them APs, reach the presynaptic terminal, usually within milliseconds of each other, right? Just a few milliseconds. So I think that this is best exemplified by panel A here, right? And so this is the presynaptic membrane potential here, presynaptic. And then we're going to stimulate, right, presynaptic, and measure a change in postsynaptic. So this is postsynaptic. So an action potential is generated in the presynaptic cell here, right, near each threshold and all that. We know all about this. And you can see that this single action potential elicits a particular EPSP. This EPSP is not particularly great, right? So in the postsynaptic cell, this one small EPSP relatively, right, changes the membrane potential about 2 millivolts. So again, we're depolarized, we're getting towards threshold right here, but this generally only moves us about from minus 65 to minus 63. So we depolarize, right, which is what we would expect in the postsynaptic cell. But that depolarization, about 2 millivolts. Remember that generating an action potential in the postsynaptic membrane is typically the response of a whole bunch of incoming signals, right? Not just one. But I think this is maybe worth writing down. At least some of this is, right? That as expected, right? This is what we know would happen, that a presynaptic action potential causes a postsynaptic EPSP. That is, we're going toward threshold. And you can see the timeline of this matters, right? That our time frame is only, and we're in chunks of 10 milliseconds. And when the presynaptic cell is stimulated again, so it generates an action potential here, and then when it's stimulated, generate another action potential, we see a second EPSP in the postsynaptic cell here. But that EPSP is larger than the first one, right? That this region here, right, is increased, and this is facilitation. So when the presynaptic cell is stimulated again, or generates a second action potential, and again, right after, and we'll talk about how the timing of this matters, right? When it generates a second action potential, the magnitude of the EPSP, right, of corresponding EPSP increases. Okay, and we think that this is due to calcium entry, right? That if, I'm going to go up here for this, right? So if we had one axon terminal that was synapsing, right, pre and post, the idea is that calcium, right, flowing through voltage-gated channels goes up in the axon terminal really quickly, but it doesn't go away nearly as quickly. So by the time a second action potential arrives, there's already calcium, sort of residual calcium, already present. Okay, and that's why we see this type of synaptic facilitation. I know that this term, right, if we go up here, within milliseconds of each other, the question is, well, how many milliseconds can be between these stimuli before we get rid of synaptic facilitation, before we don't see it anymore, right? And so I think the last point that we'll make about this is that it's time dependent. And so in B here, what you're seeing is the interval between stimuli and the amount of facilitation. So after 10 milliseconds, right, in cells, right, we changed and facilitated by about, 0.5 millivolts, okay? But by the time we got out to 50 milliseconds, there was no real change at all, right? So I think rather than saying it only works for this amount of time, we could just say that it's time dependent, and that synaptic facilitation decreases over time. And certainly by 50 milliseconds, this effect is pretty much gone.